The comparator. This is a 741 circuit. As you guys can deduce from the name, the comparator is a circuit that compares two values together. Now, as we're using the 741, comparing two voltages. Circuit diagram. That's my positive supply volt. There I've got my negative supply volt. And then my inverting and my non-inverting inputs are going to connect to a voltage divider circuit. This voltage divider circuit is going to divide my supply voltage into two sections. Comparator is going to have a reference voltage caused by a voltage divider circuit that's connected between the supply voltage. We've all seen this type of circuit configuration, or the effects of this circuit configuration, in devices like automatic light switches and automatic wipers. The output is going to connect to a device or memory element, and then my input over here, this is my actual input. Okay, this input also connects between the positive and the negative supply, but in the sense that we will have a sensor somewhere, either on the top there or the bottom there. So that's my V in, and V in will connect between the positive and the negative, between, let's say for example, a resistor and a light dependent resistor, as an example. Other possible devices that can be used, thermistors or strain gauges, but any device that changes its voltage according to external influences. The operation of the circuit: resistor 1 and 2 will generate a reference voltage on my non-inverting input. So if we look at the graph there, okay, R1 and 2 generates a reference voltage on my non-inverting inputs. I can adjust that by changing the resistance of those two resistors. Now if I go and connect an input voltage, let's say for example just a simple triangular wave like that, okay, we can see at this point we've got a voltage less than my non-inverting input. As a result, this is V in. As a result, what's going to happen on the output, V out is blue. So at this stage, my non-inverting input voltage is larger than my inverting input. As a result, my output will switch to the positive saturation, and it will remain there up to that point over there. Once that point is reached, my inverting input voltage increases or goes above my reference, and as a result it's going to switch into the negative saturation over there, and it's going to stay there until we get to that stage whereby the reference voltage or the non-inverting voltage is larger again, and then it'll switch back to the plus V, or the positive saturation, out of the negative saturation stage. Okay, this input signal can be any signal. You can connect it to a microphone if you want, but that will be my cutting limit. Anything above that, I will have a negative voltage on the output, and anything below that I will have a positive voltage. Now if I were to switch these two, input. In other words, if this was my non-inverting input and this was my inverting input, then the effect would be, if this is my exact same input scenario, only difference is that's my inverting input, then this output signal will be upside down. In other words, it'll stay off, and once my input goes above the reference voltage, my output will then switch on. The Schmitt trigger is a bistable multi-vibrator, which means it's got two stable states, and it operates as a combination between the bistable and the comparator. It looks at the input values and switches according to the outputs, but where the comparator switches at a certain voltage level, if it's above that level it switches one way, if it's below that level it switches the other way. The Schmitt trigger goes and adds an additional level so that it switches on at a certain voltage and it switches off at a separate different voltage. This is called the hysteresis effect of my multi-vibrator, or the Schmitt trigger. This hysteresis curve, hysteresis means to lag behind, is a simple explanation of how this circuit obtains the ability to do that type of switching. Now the axis is dependent on the supply voltage and the values of the components. Okay, so on the horizontal axis over here I've got the value of my input voltage. On my vertical axis I've got the output voltage. Okay, where that would be the value of plus V and that would be the value of minus V. Okay, now because of the circuit's construction it generates these two levels, which is my lower trigger point or my lower trigger value, and also my upper trigger value or upper trigger point. That's all due to the construction of the circuit. Let's have a look at how the circuit is built. Again, we've got the voltage divider generated by two resistors to form my reference voltages. Call this R1 and that one R2. Okay, this point over here connects to my negative supply voltage, and that point there connects to the op amp on the non-inverting input. That output connects over there, and I've got a feedback resistor that connects between my referencing resistors. My inverting input is just my input, and then I've got the positive supply connected over there, and I've got the negative supply connected over there. Okay, now I must remember that V out is either equal to plus V or it's equal to minus V. Now if this is equal to plus V, then I must remember that this point is now aligned with that voltage, which means I've got this configuration where R2 is in series with R1 and RF in parallel with each other. if my output is equal to minus V, then minus V aligns with this, which means this point now becomes minus V, and as a result R1 is in series with the combination of R2 and R3 R2 and RF in parallel with each other. Okay, now how these two work is the resistors R1 and 2 together serves as a voltage divider circuit between the supply, which is the positive and the negative, and the feedback resistor will develop a voltage in accordance with R2 and R1's voltages as well as the output. When the input moves below this voltage level that is generated by RF, then my output will switch on. When the input goes above that level, then my output will switch off. So looking at the graph for this, if this is my input signal, let's draw something silly like that. If this is V in, it'll have two cutting levels, let's say over there and over there. This is my lower trigger point, that is my upper trigger point, and we're comparing this to the output voltage, where this is the level of the positive saturation and this is the level of the negative saturation. Now at this point, the moment my input switches above that level, it is going to force my output to switch to the low state or negative saturation, and it's going to stay there until it reaches that point there where it meets the lower trigger value. When it reaches that lower trigger value, my output is going to switch back into the positive saturation, and it's going to stay there until it reaches that point there. There is the positive saturation, or where it switches out of the positive saturation because the input is above that level, and then it switches to the lower saturation. Now what we see, it's going to stay in the lower saturation all the way until it crosses that lower trigger point again. So, okay, upper trigger level is equal to R total multiply upper trigger level. To do those calculations, R total is the sum or the product of R1 and RF divided by R1 plus RF, because remember they are in parallel with each other, because they're in parallel and in series over there. That's where this part of the formula comes from. R2 divided by R total plus R2. That calculates the gain of the feedback value, or the percentage of the feedback value, that's beta, and then multiplied with my output value to get the voltage over there. Okay, when I'm working with the lower trigger level, the ones over there is going to become R2, and the R2s over there are going to become R1, because now RF is in parallel with R2, and those two together are in series with R1.